Okay, so you asked about hanging wall and footwall. Any other question? So I told you that the actual fault is a plane. Come. So there are two sides of this plane. Let us say this is one side, the other side is this plane. Sometimes this may be visible at the surface, sometimes this may not be visible at the surface. The fault may be buried deep down under the soil, okay, and rock. So this may be quite deep, or sometimes you may see it at the surface of the earth. We call it surface expression of fault. So fault may be expressed at surface, it may not be expressed at surface. And this angle may be different, okay? So if you try to stand on this fault, then the side, the face of the fault on which your foot will be there, where you will be standing, okay? So this is foot wall. And the other wall is hanging wall. If you consider opposite to this type of fault, then naturally this will become foot wall and this will become hanging wall. Because this angle is not 90 degree. If the angle is exactly at 90 degree, then it will be difficult to define which one is the foot wall and which is the hanging wall. But usually you will not get 90 degree. Either it will be inclined this side or it will be dipping this side. So depending on in which direction this is dipping and whether your sight is on this side or your sight is on this side of the fault, the intensity of shaking may be different, okay? Or if the sight is along this fault, then the shaking will be different. So shaking also depends on which direction your sight is in comparison to the fault, okay? Then we discussed that an important point here is estimation of fault potential. How large, what magnitude earthquake can occur? On a fault. Okay, so how we can decide what magnitude earthquake can occur? One way is from the past earthquake records. So if an earthquake has caused an earthquake of magnitude 8, let us say, in the past, there is always a chance that magnitude 8 earthquake can occur in future also. Okay, so whatever records are available with us, but here the records are available for a very small duration. So records are available, if instrumented records are there, for 60 years, 70 years. And if we take into account the historical record also, so in historical documents there may be some mention of that earthquake. So based on that also some assessment can be made. So if we take that also, then it may be for some 100 years, few hundred years, okay? Whereas here we are talking about earthquakes which have several thousand years return period, okay? So it is difficult to conclude based on that. Then we can do it what we call paleoseismology. Okay, in paleoseismology, they look for geological evidence So if an earthquake has occurred in the past, it must have caused some deformation in the ground. Those deformations are preserved inside the soil deposits. So the geologist, they dig there, they make trenches, and in those trenches they try to determine what order of displacement has taken place at a certain location. And based on that, they try to estimate what size, what magnitude earthquake might have occurred at that fault. Then it is based on geometry. To release more energy, a larger fault rupture is required. Larger the size of the fault rupture, the length of the fault which has ruptured, larger will be the magnitude. Okay. So for example, in case of Nepal earthquake, which was how much? Anybody remembers?
20.
No, I mean, what was the magnitude? 7.6 or 7.9, something in that range. Okay. So in that earthquake, the rupture length was about 250 kilometers. So 250 kilometer fault has ruptured. So huge lengths of the fault rupture are required to have large earthquakes. So if we have an idea that how much length of the fault is there, what length can rupture, so based on that also we can calculate. Okay, so there is a very useful relationship given by Welsh and Coppersmith that is commonly used. How to go into, yeah, okay. Okay, so what you see here, the magnitude MW, this W stands for moment magnitude. Okay, there are different scales of magnitude. You have heard about Richter magnitude scale. That is one scale. There are other scales also. One such scale is moment magnitude scale. So that is based on the moment of the fault rupture which has taken place. So this moment magnitude is considered to be the most reasonable scale, and currently almost all calculations they are using MW. So Wells and Coppersmith, they have determined for different faults what was the magnitude potential of those faults and what is the length, area and displacement. So they have calculated these relationships based on regression. So past data, they have fitted the curve and they have got this. And here you see different types of fault mechanism are there. If it is strike slip, reverse or normal. All means that where they have not differentiated between the mechanism, they have considered all the data. So then this relationship you can use when you do not know about the fault mechanism. In many cases the fault mechanism may not be known, that what type of fault really that is. So if you know it, you will use the corresponding relationship. If you do not know it, you will use this. If you know the length of the fault, you will use this relationship. If you know the area, then you can use this. If you know this capital D is the displacement which is occurring at that fault due to rupture. So this is rupture displacement. Okay, and moment magnitude is based on moment of earthquake. So what is moment of earthquake? So moment of earthquake is tau into A into D. So what is tau? Tau is the shear strength or shear stress at the rupture plane. Okay, A is the area, tau into A is what? Multiplied by D, which I just told you is the rupture displacement. How much movement is taking place during earthquake? So what is this quantity giving us? Energy or moment? Force into displacement is energy. So actually it is representing energy, but you can see its units are same as that of moment. Moment also is force into lever arm. Okay, so it is called moment. Actually it is a measure of the energy released during the fault rupture. Okay, so it cannot be obtained directly. It is difficult to obtain, so complex calculations are done. On the other hand, the Richter magnitude, okay, or we also call it local magnitude, that can be obtained more directly from the measurements. So first you get the Richter magnitude, but all the scientific calculations are done in terms of moment magnitude, and the moment is defined like this. Actually it is a measure of energy released, and I told you that this magnitude we are defining to quantify the energy released. Okay, so either it can be represented in terms of magnitude or it can be represented in terms of energy. So how many tons of TNT, okay, the energy has been released. And when the magnitude increases by one number, the energy increases 30 times. Increase of 1 unit in magnitude corresponds to 30 times increase in energy released. So an 8 magnitude earthquake will have how much energy as compared to 6 magnitude earthquake? 900 times, or roughly 1000 times. So 1000 times energy will be released in 8 magnitude earthquake as compared to 6 magnitude earthquake. Okay, so scale of magnitude is logarithmic scale, but it is not 10 times. Okay, it is 30 times the energy released. So we can get an idea of that based on the geometry of fault. So this relationship we will be using in the example problem which I have given in the assignment. Then we can also get this from seismotectonic evidence. What is seismotectonic evidence? The different plates are moving towards each other or away or sliding. If we can measure that movement, we will know how much energy, because finally the source of energy is what? Movement of those tectonic plates. So if we can measure the movement of those tectonic plates, we can relate it with the magnitude potential of the fault. So there is a relationship given by Ruff and Kanamori. In 1980. So they have given MW as minus 0.0089 T plus 0.134 V plus 7.96. Here T is the age of rock in million years, and V is the rate of convergence in centimeter per year. Why the age of rock should come in calculation of magnitude? So, strength of the rock will be governed by its age, tau, okay, will be governed by this. And V is the rate of convergence by which one plate is moving towards the other. Okay, for example, our Indian plate is moving towards Eurasian plate. It is converging towards Eurasian plate. Okay, how we can determine by what speed it is moving? Nowadays it is much easier using satellite imagery or GPS stations. So along different faults, people are doing different measurements. So you just need to put two pillars, one on this side of the fault, another on this side of the fault, keep on measuring the distance between them, but it has to be very accurate. It is to be measured in centimeter per year. Okay, so you should be able to measure in millimeters. So that accuracy of the GPS is needed. The GPS has to be really very accurate. It should be able to measure in millimeters. Okay, so all of you have GPS in your mobile phone. What is the order of accuracy there? 100 to 200 मीटर. फिर तो आप जहाँ जा रहे हैं उसके बजाय कहीं और पहुँच जाएंगे. Any idea what order? Okay, of that order. So you can think how difficult it is to get in centimeters. You require special instrumentation for that, but that is possible to measure. Any idea what is the convergence rate of Indian plate towards Eurasian plate? 2 centimeter? Any other guess or anybody else? Between 5 to 7 centimeters in that. So 5 to 7 centimeters per year, our land is vanishing. So we are losing our land by about 7 centimeters, but we need not to worry about that. In terms of the land vanishing, we have to more worry about earthquakes. So the energy, this 7 centimeter in a year, how much energy it is storing on such a huge land mass, that is important. Okay, and based on this, one can estimate. So there is a theory what we call gap theory, that this energy which is accumulating should release. So they do an energy balance. How much energy is accumulating, how much energy is being released by different earthquakes. So if we know all the earthquakes occurring at a fault, so we know in a given duration how much energy has been released. So we can sort of estimate that when and what magnitude of earthquake we are expecting. Okay, although getting record of all the earthquakes and this energy is very difficult, so nobody has been so far been able to predict that when and what magnitude earthquake will occur, but that is one way of looking in that direction. Okay? So now please look at your tutorial sheet. I have already given you a question there on DSHA.
By calculating the amount of energy stored or accumulated, you can at least say that this much amount of maximum earthquake or damage can happen at that fault or from the energy.
People are saying many things. There is a very famous study by Wilhelm. Wilhelm or Oldham? I always get confused between these two gentlemen's name. So a UK scientist is there, Wilhelm. He has done some study and he has predicted that in Himalayan region where the seismic gaps are there. Okay, but this phenomena is, you are talking about here thousands of years, millions of years, that way you are talking. So it is very difficult to predict when it will happen. Okay, so seismic gaps along the Himalayan arc have been already identified. So where energy imbalance is there, energy is getting accumulated. Okay, and I do not know if you are familiar with the geography or here or not. In the Kumaon region, Pithoragarh region, there is larger chance of having a large earthquake. So more energy gap has been obtained there. So please take out that question, look at it. Yeah.
Various methods of energy release, which one is we use most to
Energy release? I couldn't get.
We have calculated magnitude released. You told this is formula MW.
Uh-huh.
Before that, we were talking about moment of earthquake. That was also the measure of energy release.
Right.
So then, when we have to describe about the magnitude of the earthquake, which one is?
So which scale, which method of measuring energy is more accurate? That's what you mean to say. I told you now, this MW, moment magnitude, that is considered to be most accurate. Other than MW, there is Richter scale ML, there is surface wave scale MS, okay, and there are few other scales. So most commonly used are these. So nowadays we use MW.
But it is empirical.
MW, anything is empirical. There is no way to measure the energy. When earthquake is occurring, there is no way that you can put an energy meter and get the energy. It is not, no such meter exists. What you measure is only acceleration. And from that acceleration, you try to get the inverse information. You try to estimate how much energy might have been released. Based on that, you calculate the magnitude. So if you have to measure earthquake, you have only two instruments, seismograph and accelerometer. So these two equipment only you can use. Whatever information you are deriving based on these two measurements. There is no other measurement of intensity or energy released which you can get. Okay, so please look at this question number 6. So there are several faults. Some faults are line fault and a few or one is area fault. So can you tell me the steps? What will be the steps to determine PGA or SA at a given period at this site? Yes? How you will proceed? You know the length or area of the faults. From those lengths and area, what you can get? Magnitude, using Welsh and Copper-Smith relationship, which I have shown, I have also given you. Okay, in the soft copy also I have given you. So you can get the magnitude. Now what next? Yeah, these are all active faults. Because identifying active and passive faults is not easy. For that you need a lot of seismological information. So these faults which are given, these are all active faults. So what will be the next? Magnitude you have got. Then the distance between the fault and site. How you will obtain that distance? Shortest distance? Why shortest distance? Okay, so suppose shortest distance is given, or you can obtain from here. What next? Yes? Then you need a relationship between the intensity, magnitude and distance. Okay, such relationship we have discussed earlier, attenuation relationship. Lot of attenuation relationships are available. I will give you just some simple ones. Okay, those are not used anymore. The current attenuation relationships which we are using are much more complex. Okay, I am giving you the simplest one. And the form of all these equations is like this. Y is the intensity parameter which you want to determine, and it is a function of m, r, okay, and the path characteristics. So one simple relationship was given by Campbell in 1981 based on worldwide data. So two things are important when you are using, or rather three things are important when you are using any attenuation relationship. First of all, which data has been used? Okay, I told you that the attenuation relationship will vary from region to region, country to country. Okay, because it depends upon the characteristics of the crust, earth crust, through which the seismic waves are traveling. So which data set has been used? So in 1981, I told you that the measurement started 1950s or 60s, and in 1981 not so much data was available that they can come out with specific attenuation relationships for different parts of the world. So this is one of the first relationships which was developed, and they considered whatever data world over was available to them, and using that they came out with this relationship log PHA in the units of G. PHA, peak horizontal acceleration. It is nothing but EPGA, effective peak ground acceleration. That is equal to minus 4.141 plus 0.86 m minus 1.09 log of r plus 0.0606 exponential 0.7 m. Okay, this is the simplest relationship. So you can imagine what will be the complex ones. Fortunately, you need not to remember it. It will be available to you in the exam. You need not to cram these. Here, m, this is very important. Which definition of m has been used? Like you were asking that which scale we use. So what is this m? It is important. Which definition of m has been used? So this is local magnitude. At that time, that was the common scale. Local magnitude means Richter scale. So for m less than 6, and m is surface wave. Magnitude for m greater than 6. So it is important that which definition of magnitude has been used. Similarly, it is also important that which definition of r has been used. So r in this case was closest distance from site to fault rupture in kilometers. The units are kilometer. Okay, and they also, when they fitted this, they also calculated sigma, the variance, okay, standard deviation. So sigma of log PHA is 0.37. So this is one relationship which you can use. It is based on magnitude and distance, and because it is based on worldwide data, so it will be applicable worldwide. Of course, it will be approximate. There is a lot of variation, okay, and sigma in log PHA is, we will be using this also. I will explain you later where this will be required, okay. So this sigma in log PHA is 0.37. This is given in Kramer's book. I have taken from there only. You can find from there. This is one relationship. Just to give you a feel how these relationships look like. Then second relationship given by Bohr in 1993. By that time some more data was available, so they used a regional data, and that was for North American. North American means Canada, US, okay. And this is valid for distance less than 100 kilometers from surface projection of fault. Okay, so you will project the fault to the surface and then take. Some of the relationships which are now, they are taking the distance from the either perpendicular, normal to the fault. So those are considering the fault, 3D fault inside the earth, and distance they are taking from there. So different definitions of distance are available, different definitions of magnitude are available, and then these relationships have been developed using different data sets. And whichever data sets has been used for regression, same you can use, only same region, these are valid. It will not be valid in other parts of the world. And the relationship is like this: log to the base 10, that was natural log, okay? PHA in units of G is B1 plus B2 MW minus 6. MW means moment magnitude, plus B3 MW minus 6 square plus B4R plus B5 log of R plus B6 GB and B7 GC. And R is given as square root D square plus H square and D is the distance from surface projection of fault. So this is D. What is H? H is a parameter which is in a way representative of the depth of the rupture, okay? And based on their regression, they have given coefficients V1, B2, B3, B4, B5, B6, B7, and two values they have done. They have given one they are calling random and another one they are calling larger. Can you guess what this random and larger means? These are the components of earthquake. I told you earthquake has two horizontal components. So these are for PHA, horizontal component only. So in horizontal component, one possibility is that in each ground motion, you take only the larger component. Okay? So now which component will be larger? If I give you two records of earthquake, let us say one is north-south, another is east-west, which one will be larger? How you will determine which one is larger? Two ground motion records are with you. Can you tell me which one is larger? Larger? Larger क्या? Peak ground acceleration. Okay. So one way of identifying larger magnitude is which is having larger PGA. Okay. But larger PGA doesn't mean that the response spectrum will also be larger. Okay. It is possible that one earthquake is having lower PGA, but in a range of period, it may be having higher values of response spectrum. Okay, so that limitation is there. When they are saying larger component means larger PGA they have done. Okay, so random means what? They have considered both the components. So randomly it may be larger or smaller, all they have considered, and larger means they have considered only the larger component. So they have performed regression between larger components only, or they have performed regression without considering which component is larger or smaller. They have considered all the components of earthquake, whatever measurements were available. So for random component, this value of V1 is minus 0.105, 0.229, 0, minus 0.778, 0.162 and H also 0.162, not 0.62, 0.251 and 5.57. Again, I have taken from Kramer's book. You can even refer to the original paper. For larger component, 0.038, 0.216, 00, minus 0.777, 0.158, 0.254 and 5.48. Slight difference between the two you will find. Okay. Now here you see that two of the coefficients are 0. Then why these are there? So first, the form of this equation was obtained, okay, based on physics, and then regression was done. So for this particular data set, the values of B4 and B5 may come out to be 0, but for some other data set, these may not be 0. So they have retained the form. The coefficients they have worked out for this particular data set, it came out to be 0. Okay. Then with V6 and V7, there is another factor here, GB and GC. So what are these GB and GC? These are representing the site class. So the site classification is done in this relationship into three classes, A, B and C, and it is based on average shear wave velocity in top 30 meters. We call it VS30. So this is shear wave velocity. What is shear wave velocity? Vs. We discussed this earlier also. So this is square root G by rho. The velocity by which shear wave is traveling. Okay. In case of earthquake, shear wave, the secondary wave, as compared to primary or compressional wave, that is having higher intensity, that is carrying most of the energy. So we consider the shear wave velocity. And what is this site class representing? It is representing the amplification. If the site class A, actually site class A is representing rock, and the shear wave velocity is greater than 750 meter per second. So this is rock, a hard site. So that is considered as site class A. So you can see here in this relationship there is no GA. There is only GB and GC. So A is the GA, or site class A is the reference site. Okay. Site class B, which is having 360 to 750 meter per second shear wave velocity. Okay. So this is a medium type of soil, and C 180 So 360. You can ask me why we are considering the top 30 meter. The shear wave velocity in top 30 meters. So is shear wave or earthquake waves traveling in 30 meter? Yes. That will cause more damage. What will cause more damage?
But top surface of
Because the
Earth
buildings.
is
Hmm?
top surface of Earth is
Top surface of earth is?
within the depth of 30 meters.
Yeah, so why you need 30 meter?
Because we can measure up to 30 meters.
Okay, so first of all, why only 30 meters? Why not 40 meter? Why not 20 meter? That is one. Secondly, why top 30 meter? Why top portion only? In general, if you look at the soil surface, there will be layers, and at some depth there will be bedrock. Okay. Originally when the crust was formed, it was all rock. Due to weathering of rock and transportation due to water and air, the soil deposits have taken place. So below there is rock, above that there are soil layers. So when the rupture is occurring here, the wave is traveling in this bedrock. Okay, and then it gets transmitted through this to your site. Here you are constructing your building. Okay, so it gets transmitted through this soil. The characteristics of the wave which you are going to get there will depend upon this full height which you are getting from the bedrock, full depth of the soil. That will decide, okay, what will be the characteristics here. Generally, what is happening here, in the bedrock, the shear wave velocity will be larger. In the soil, the shear wave velocity will be less. So wave will be propagating faster here and slowly here. So when wave is propagating faster up to a point and then the speed delays, what will happen to the energy? Energy is coming at a rate. Energy cannot be stored or destroyed. It has to pass. So what will happen? The intensity of energy will increase. Okay? So when it reaches this medium, there is increase in the intensity. Okay? And intensity, how we represent intensity? In terms of PGA. Okay? So the PGA or the amplitude of motion will increase. So here the velocity will be faster, amplitude will be smaller. Here the velocity will be lower and the amplitude will increase. As a result, the intensity which you are going to get here will be more than this. Okay? And you can think of a situation like this. Okay, and earthquake is occurring somewhere here. So two sites are there. One is here, another is here. So the earthquake motion is reaching like this. When it will go reach here, suddenly its amplitude will increase. Why it will increase? Is soil adding to energy? I told you that the dissipation is, first of all, why the earthquake is not coming like this? Why it has to first go and come like this? Why it can't from here go like this? When earthquake is occurring at a fault, the energy will be transmitting in all the direction. It's not that it will be focused along a particular path and it will go like this. It will be going in all the directions. But those rays, those waves which are transmitting in soil, will die down very soon. So within soil, it cannot travel long distances because soil is causing larger attenuation. Okay? So damping is more in the soil. So energy will dissipate much faster. With shorter distances, it will die down, it cannot reach the site. In the rock, the damping is much slower. In the rock, it can travel long distances. So from the fault, it will be first, or only those rays, those waves will reach my site which are having their longer path in the rock and shorter path in the soil. Those which are having long path in soil itself, those will not reach. Those will die down before that. Okay, so it's not that earthquake is following a particular path. From here, the energy is going in all the directions. When energy is being released from the fault, it is being transmitted in all the directions, in 3 dimensions. Okay, that ray which will transmit maximum energy to my site, that is of importance to me. So this direction, this will be transmitting maximum energy to my site. As compared to this energy will be much less because it is having long distance within the soil, and soil will actually dissipate the energy. So in reality, soil is dissipating the energy. Okay, but here what we are seeing, there is amplification. So this we call soil amplification or site amplification is more appropriate word. So why the amplification occurs? Soil is actually causing damping. It is causing dissipation. It is dissipating energy. But we are saying it is getting amplified. And example of this was the first earthquake which brought it into limelight was Mexico earthquake of 1984. It will take some time, huh? Maybe if I copy on this, perhaps it will be faster. Okay, so this is Mexico City. Okay, and earthquake occurred some 350 kilometers away from here. Now, when we were talking about seismic hazard estimation, we said that we will consider faults within 300 kilometers of radius. Why 300 kilometers only? Because if an earthquake is away from that, it is not expected to cause any damaging effect at my site. Here, earthquake occurred at 350 kilometers. Still, it caused a lot of damage in Mexico City because of a special condition. And that special condition was that Mexico City is situated on the dried bed of a lake. So here you see how the depth of the deposits, soil deposits, lake bed you can consider as soft soil, and the depth will vary, depending on the shape of the lake, the depth is going to vary. So depth of the deposition, these are the contours of the depth. So you can see, so on one side of Mexico City there are foothills. So here these are foothills. Foothills means what? The rock is at the surface. So rock outcrop also we call it. So at the surface itself it is rock, and then slowly in this direction the depth is increasing. So here it is 20 meter, here 30 meter, here 40, 60 and so on. And there were 2 stations also, recording stations also in Mexico City. One here at the University of Mexico, UNAM, which was on foothills. Another one here, SCT, this is somewhere 20 to 30 meter deep deposits. were there. So recording was here also, recording they got there also. Here are the records plotted on the same scale. So what you have got on UNAM is this, and this is what you have obtained at SCT. Okay, so at UNAM it's very small. In the beginning also I have shown you this earthquake when we have compared different earthquakes. So the amplitude as expected at 350 kilometers, it should have been very small amplitude, very low PGA. Okay, and that PGA might not have affected our structures. So very low PGA is expected here, but at SCT you can see that PGA has increased. Okay, so what caused this increase?
Transfer of energy to the
How energy has increased?
the velocity is increasing.
So energy has not increased because the energy was getting transmitted at higher velocity, and then it is like people are coming in one direction and suddenly the velocity at the end, you are passing on a bridge, and suddenly at one end of the bridge there is a stoppage or velocity is reduced. What will happen? There will be force from below. Okay, so that happened, and because the energy was coming at higher rate, and in the soil it cannot be transmitted at the same speed, so more energy, okay, has to, or more amplitude has to be there to pass on the same energy. So due to that there was increase in amplitude. That is one aspect. The soil also passes, or soil itself is behaving like a structure. So you remember when we were talking about building has several mode shapes, and fundamental mode shape is having maximum contribution, and if you have to look at the top of the building, the acceleration or the motion will be, or building will be moving mostly in its fundamental mode. Same thing will happen in soil also. Soil layers, those are also vibrating. So that is like a building storage. So it has its own period. Soil also has own period similar to the building. So corresponding to that period, those frequencies which were close to the frequency of the soil, those frequencies, those harmonics will get amplified more. Okay, other frequencies will die down. What will happen? The energy from those frequencies will be taken up and will be transmitted to these frequencies. So this phenomena we call filtering. So soil has two actions: amplification soil causes amplification, and it causes filtering. Similar behavior you will expect by a building also. So this is building, this is soil. Very similar. So here also the motion is traveling, here also the motion is traveling. So at the top there is larger amplification, roughly 2 times of what you are getting here. Here also it is roughly 2 times of that. Okay, and it can be more than 2 times depending on the shear wave velocity here, because it is causing slower speed of transfer of energy. And depending on what is the frequency of this column, soil column, imaginary column of the soil we can take. Okay, so it will depend upon the stiffness and mass. As you increase this dimension, the mass and stiffness will increase in the same proportion. So frequency will also increase in the same proportion. So if you consider any such width, unit or otherwise, and take the period of this, it will be same as the period of the whole soil layer. And this period can be simply given as 4h by Vs, where h is this height and Vs is the shear wave velocity, average shear wave velocity in this column. So the period is roughly 4h by Vs. So corresponding to this period, there will be filtering action and it will get amplified. That you can see in case of Mexico, if you look at the response spectrum. So if you look at the response spectrum, this is what you are getting at UNEM. So at UNEM, you can see that PGA, EPGA on rock is how much? Less than 0.05. This is 0.2, this is 0.1, this is less than 0.05. What is the Z value for our zone 2? We have 4 zones. Zone 2, zone 3, zone 4, zone 5. What is the Z value for zone 5, let us say, largest? 0.36. Zone 4? Okay. Zone 3? 0.16. Zone 2? Okay. So it is much, that is our lowest zone. So it is much less than that. That's what was expected at 350 kilometers. So at 350 kilometers, it was expected to be much lower, and it is much lower. Even the maximum spectral acceleration is less than 0.1 g. So it will hardly cause any damage. It is not of concern. But if you look at SCT, there is amplification of PG itself. PG itself is now more than our zone 2. And more than that, there is spectral acceleration of 0.8 g. What is the peak spectral acceleration in our zone 5? Peak spectral acceleration, maximum spectral acceleration in our zone 5. 2.5 into 0.36, how much that becomes? 0.9. So you can see it is close to that. In zone 4, 0.6. It's more than our zone 4. It is close to our zone 5. So at 350 kilometer, where nothing was expected, nothing should have happened, and actually at UNEM, it tells us that the intensity is very, very low. But in Mexico City, at this station, it is 0.8 g, as high as the most or the highest seismic zone in our country. Okay? And you can imagine then what can happen. There was large damage. Okay? But this damage, you can see here it is much wider. You can see that in whole of this range of the period, the PGA is larger. But here the peak of the spectral acceleration is occurring in a narrow range of period, roughly close to 2. Okay? How this can be obtained? This can be obtained using this formula 4h by bs. The shear wave velocity there is 75 meter per second. It's very loose soil. So 75 meter per second, and height we have just taken. Okay, so 37.5 meter was the depth exactly at the location of SCT, and if you calculate, it comes out to be 2 seconds. Okay, so here the peak was observed. And those buildings which are having period close to 2 seconds, those will be subjected to very large damage. Which height of the buildings are expected to have 2 second period? How many stories? Roughly 20 story, you can say 0.1 n. Okay, and 0.1 n is the elastic period. When these get damaged, the period will elongate. So it was observed that the buildings between 5 to 20 stories, those were suffered lot of damage. Those buildings which were having period or height less than 5 stories, those were here. Nothing happened. Those between 5 to 20 stories, those were here. Which were more than 20 stories, and what happens? During earthquake, the period increases. After cracking, the period increases. So those were here. And actually the period you will see is more than 0.1 n. So 5 to 20 story buildings, those suffered lot of damage. Because of this phenomena, it is site amplification. It consists of two things: soil amplification and soil filtering. So filtering of the frequency, those frequencies which were matching with the frequency of the soil column, okay, those were amplified a lot. And it doesn't mean that the soil has added energy. In reality, the soil is dissipating the energy. Okay, but there are two phenomena occurring in the soil. One is that the velocity is reduced. 75 meter per second in bedrock, it will be 750 meter per second. It is 75 meter per second, 1/10. So you can see that there will be lot of bottlenecking, okay, of the energy, and due to that the amplitude of ground motion will increase. So this is to some extent taken into account in Bouret's relationship.
Basically rock structure, the underlying soil was basically rock, so the wave traveled and then the soft soil amplification happened.
So wave traveled a long distance in the rock. 350 kilometers it traveled in the rock, and then 30 meters it traveled in soil. So that 350 kilometers when it was traveling, it got attenuated there also. Okay, so that's why even at UNAM, the amplitude was very low because that was in rock. But what happened? As it entered into the soil, the 30-meter soil, last 30 meter, it had to travel in soil. So when it entered to that last 30 meter, then lot of accumulation of energy took place, and due to that, the amplitude increased. And filtering of that also took place. Same, similar. Okay, so resonance is when we are having harmonic motion. In case of earthquake, there is not harmonic motion. It is not single harmonic. There is a range of frequency. So there we are talking filtering, that those frequencies in the ground motion which were away from the frequency of the soil, those were energy from there will be taken and it was given to those frequencies which were close to the frequency of the soil column. So this phenomena occurred within the soil. So Bouret's relationship tries to take that into account in terms of these coefficients GV and GC. So GV corresponds to the medium soil, GC corresponds to soft soil. There is no GA because that is the reference site. The attenuation relationship has been developed for that site. So this GV, that is equal to 0 for site class A. It is 1 for site class B, and it is 0 for site class C. And GC is a 0 for site class A, it is 0 for site class B, and it will be 0, sorry, not 0, 1 for site class C. So in case of site class B, parameter B6 will be added, okay, because this will become 0. In soft soil, this will become 0, this will be added. And you can see here, B6 is 0.158 and B7 is 0.254. And in case of site class A, none of them, both of them will be 0. So as compared to site class A, in site class B, the PGA will be higher. This is to be added in log. So 0.162 addition into log of the magnitude. So that will be a significant increase. And then in case of soft soil, B7 will be added. Okay. So this is the first of these modern equations which have been given by Bouré. After this, a lot of development has taken place. Nowadays we are using NGA best 2. Okay. Before that, there were NGA best 1. I think 2008 NGA best 1 came and 2014 NGA best 2. You can check, I do not remember. If you give search, you will find this. So this best, actual NGA means next generation attenuation relationships. And best is representing 4 groups. So name or letter of, or the first letter of the surname of the 4 authors who have written that. So it is not west direction. Okay. It has one interpretation there also, because the data they have used is mostly from western coast of US. Okay, because western coast of US, that is more seismic. Eastern coast is not seismic. California region, that's the most seismic, and lot of instrumentation and results are available from there also. Although they have used worldwide data, they have used KickNat, that is Japanese site, so they have used data from there also. So this is not representing west direction. This is just the name of the 4 authors. But popularly, this is known as NGA best 2. Earlier, this was NGA best 1. They have further improved NGA best 2. So hundreds of attenuation relationships are available, depending on which data set they have used, then who has done it, what definition of distance they have taken, how they have considered fault mechanism. So they are considering fault mechanism now in much more detail. They are taking into account even the effect of directivity, and also the hanging wall and footwall effect also they are taking. Whether your site is on hanging wall side or site is on the footwall side. Relationships are much complex. We will not be using these in exams, but if you are practically doing it, you will use this. Okay, and there is an open source software, Openquake, from GEM Foundation. GEM stands for Global Earthquake Model. It is available for free. You can go to GEM website. Okay. So you can look for this software. You can use it. And they have developed the hazard models for whole of the world, for India also. In India, all the sources which are available so far and their characteristics, they have put in the database. So what you have to do, you have to give the longitude and latitude of a site. It will give you the hazard at that site, considering all those faults which are there in the database. Okay. So some of you may be using it in your dissertation. And it can perform probabilistic seismic hazard assessment also. Okay. So what is the difference between deterministic and probabilistic seismic hazard assessment? The steps will remain same. You have to consider earthquake source, that means the fault. You have to consider the distance, and you have to consider the attenuation relationship. Okay, but there is uncertainty in all the three. In earthquake source, when you are characterizing that, what magnitude earthquake it can cause, there is uncertainty. Okay, so if you consider that uncertainty, if you consider that variability, then the distance, there is a variability. Okay, local site conditions, there will be variability. So if you take those variabilities into account, then you will get probabilistic seismic hazard assessment. This takes into account uncertainties at each step. So as a result, there in DSHA, what we have obtained from those attenuation relationships, log of PHA, that means PHA you have obtained. Okay. In Bure's relationship, okay, if you look in Kramer's book, okay, the same relationship can also be used, okay, for obtaining the full response spectrum. Not only PHA, but spectral acceleration at any period. Okay, so that is given, those coefficients of V1, V2, etc. are given for the full response spectrum also. I will just show you. That is so if you look at the Kramer's book, these tables are given. These tables you can see are giving the same coefficients which I have given, okay, up to h, and sigma log y, the variance is also given, okay, and these are for 5% damped peak spectral, pseudo spectral velocity. Not peak spectral velocity, pseudo spectral velocity. What is meant by pseudo spectral velocity? Omega times SD or SA by omega. And I told you, if you know the velocity, spectral velocity, you can convert this into spectral acceleration or displacement. So these coefficients, any one you need to know out of the three, the others can be obtained. So here is the period starting from 0.1 second, then V1, V2, V3. So using this, what you can do is, same expression as I have given you, same expression is to be used, only the coefficients will be used from here. And using this, you can calculate SV at different periods. Once you calculate SV at different periods, you can plot velocity response spectrum. So you can plot SV, not SA, SV versus T. So 0.1 second at different periods, you can get that, and you will get a shape like this. This is pseudo velocity spectrum or velocity spectrum. If nothing is written, it means pseudo velocity. So pseudo velocity spectrum. From this pseudo velocity spectrum, you can plot SA versus T. You can also plot SD versus T. How? Here you have to simply multiply it by, and here you have to divide by omega. This table, you can see the page number also, I have taken from Kramer's book. So this is regarding Bouret's response spectrum using Bouret's attenuation relationship and the coefficient given in the Kramer's paper. Other attenuation relationship which I was talking, NGA West 1 and NGA West 2, those are also similar. Similar tables are there. But the coefficients there are more. The parameters are not M, W and R. There are other parameters also. I don't want to take you into those parameters until unless you are doing research in that. Okay. Just to give you the process that how it is obtained. Okay. So that much should be clear that what is done. And then this last column is also giving variability, uncertainty. This will be required in PSHA. How this is obtained? This is obtained from regression. So they have got lot of data. They fitted an equation and then they also calculated variance from that fitted equation. They obtained sigma for that. Okay. So this is a major exercise in seismology to determine appropriate attenuation relationships. And for this what you need? Which data? Earthquake records. Unfortunately, for our country, although many earthquakes have occurred in the past, but this data is not there. We have not recorded our data properly. Our instruments are not working at that time. Either instruments are not there, or if those are there, those are not working. And as a result, so far we do not have any adequate data based on which we can develop an attenuation relationship which is applicable to our country. So we are borrowing. Still we are taking from NGA Best 2. Okay. That is based on North American data or Japanese data, whatever data is available to us. It is not strictly applicable to our country, but we do not have any option except borrowing that whichever is closest to our conditions. That attenuation relationship we are using. But how these attenuation relationships look like, how we can use it, that you can learn from this simple exercise which I have given you in this tutorial. Okay, any question up to this point? Yes.
साइड क्लास बता रहे थे एबीसीडीज में सॉफ्ट और हार्ड सॉइल कैसे बोल रहे थे वो?
Soft and hard is qualitative term. Okay. So how the soft and hard will be decided quantitatively? It will be decided based on the shear wave velocity. So the range of the shear wave velocity is given. If the shear wave velocity is more than 750 meter per second, okay, this generally happens in rocks. So that's why we call it hard or rock site. Then medium stiff soil, the shear wave velocity is between 360 and 750. And if it is less than 360, you have seen in case of Mexico City, it was just 75, which is very, very weak. So where we have very, very weak soil, there you will have this problem. okay, of such high soil amplification. Okay, so we take in probabilistic seismic hazard assessment, we follow the same steps, but we do statistical analysis. Okay, we consider the range of each parameter and the distribution within that range. So we take that into account. So finally we will come out with PGA or spectral acceleration or spectral velocity, but so we will get intensity parameter. So intensity, all these are intensity parameter. PGA, PGV, SA at a period, okay, SV at a period, all these are intensity parameter. So we can get these intensity parameters and corresponding probability of occurrence. Okay, so we get a value of PGA and corresponding probability of accidents, okay, or occurrence that we are going to get. Okay, so based on this probability of occurrence or probability of accidents, we define hazard labels. So hazard labels we define either in terms of probability of accidents, okay, or average return period, and then we give some name. So one is 50% probability of accidents in 50 years. It has an average return period of 75 years, and this we call serviceability earthquake SE. Tired? Should we stop? Is it becoming too much?
This is already done.
Already done? Table is already done? Good. So this is serviceability earthquake. Then 475 years, sorry, 10% in 50 years. For 75 years return period, and we call it design basis earthquake. Then we have 5% in 50 years, we call it, our return period is 1000 years. And we call it maximum earthquake, ME. And 2% in 50 years, 2475 years, or roughly 2500 years, this we call MC, maximum considered earthquake. DB and MC you might have heard earlier. Okay. Now the question is, the value given in our code, which is JED, okay, that is EPGA. Is it for DB or for MCA? dB or MC or something else?
When we divide that formula, it is dB. That formula is given in 2 by D.
Which formula?
In which Z by 2 is used.
So Z will remain Z in any formula. It can't be dB in one formula and MC in another formula. Can it be? Z will be Z, whether it is dB or MC. So is it dB or it is MC? None of them. Then what it is? You are right. It is neither dB nor MC. Why? I told you it is based on DSHA, not based on PSHA. We are doing PSHA now. So far, our code is based on DSHA, and DSHA does not give probability. So it can't be called dB or MC. The concept of dB and MC is in PSHA only. Okay, but it's not that now we do only PSHA. Sometimes PSHA can lead to erroneous result, and there we have to compare with DSHA. So there is a parity between DSHA and PSHA. So '84 percentile value from DSHA is considered equivalent to MCE, that is 2475 years return period from PSHA. Okay. How to obtain 84 percentile from DSHA? You remember when we were talking about the attenuation relationships, there was a value of sigma also given, standard deviation. So you can find, and these equations are giving you the median or average value. Okay. So average or median value you can get from the equation. But if you want to know 84 percentile, what you have to do? Median plus 1 sigma. Median plus 1 sigma is 84 percentile. Okay. In our structural design, we are using 95 percentile, 95% confidence. How much is that? Mean plus 1.64 sigma. So mean plus 1 times sigma is 84. Mean plus 1.64 sigma is 95. And like that, you can obtain from normal distribution that what percentile corresponds to which value of sigma. So you can obtain mean plus 1 sigma, that is 84 percentile, that corresponds to MC. Okay. What is given in our code is mean, not mean plus 1.64 sigma, and it has been obtained that this is equivalent to 1.5 times 50 percentile or median value obtained from DSHA. So if you know the value of sigma, you can calculate mean plus 1 sigma. If you do not know the value of sigma, you can use 1.5 into mean. Okay. So what does that mean? In our code, in our current code, So in our code, this is the response spectrum which you have seen. It is not response spectrum. It is spectral shape. And this value is not SA by G. Actually, it is SA by Z. That you keep into mind. Okay. Then when you multiply it by 1.5 Z, because Z is the median value, to obtain 84 percentile, which is equivalent to MCE, you have to multiply it by 1.5. Okay, so when you multiply it by 1.5 Z, then it becomes MCE. So actually, the MCE PGA in zone 5 is not 0.36, it is 0.54. 0.36 into 1.5. So it is 0.54. Okay, some people say that our code gives very low values of PGA. Actually, it's not that low. It is 0.54. In zone 5, it is 0.54 G. And keep that in mind, we will be comparing it tomorrow when we will meet with the PSHA also, the new code also. Then you can compare. So when you are comparing, you will not be comparing 0.36 with MCE. You have to consider 0.54 with MCE. Because this 1.5 factor is there in the code. Where it is 1.5 factor in code? Load combination. So in case of earthquake, there is no load factor. Actually, it is the correction factor to convert the mean value of DSHA into MCE. But it has been put in the load factor. And that is causing a lot of confusion to the people. They think that our code has a load factor. If you look at all other codes, the load factor, if you look at ASC 7 or Eurocode, the load factor for earthquake code is 1. Okay, because they are already considering MC or DBA. Okay, our code is considering mean value of DSHA. That's why it is multiplied by 1.5. And the rough relationship between DB and MC is 1/2. Actually, this relationship also changes. Changes, okay, from place to place. I will show you tomorrow how it is changing. Okay. It varies between 1.5 to 2. ASC 7 has a relationship between DB and MC of 1.5. So they are considering this value as 2/3 Z. What we are considering as Z/2. So they are considering the relationship 1.5. Our code is considering this relationship 2. So 1.5 by Z, 1.5 Z/2, that will be 0.75 Z. If you multiply it by 0.75 Z, this will become DBA. Okay, and if you consider Z/2, that is 0.5 Z, then it is serviceability level. So relationship, rough relationship is DB is MC, half of MC. Okay, serviceability earthquake is 1/1.5 of DB. Okay, so this is the response spectrum as per our code. And if you have to obtain for a particular site, you can obtain using Bour's relationship I have given you. Okay, if you want to obtain using probabilistic seismic hazard assessment, you need a computer tool to calculate that. You can use OpenQuake for that. Okay, we will stop here. And tomorrow when we meet, one more class on hazard, then we will finish hazard, and next week onwards, we will start talking about the structures. Okay. Any question up till this point you can ask. Was it necessary? Should we teach this portion in class or not? Or should we start? So, understand the force